Hey everyone, my name is Madeline Hart, and this is my video lab report for Lab 2, Motion of a Falling Object. In this lab, we examine the motion of an object dropped from rest using Newton's second law. Other important equations to this lab include the equation for drag force, where drag force is equal to the velocity of the object multiplied by a drag constant. We also need the equation for the force of gravity, where gravity is equal to mass times the universal gravitational constant. We also examine what a terminal velocity looks like and use the equation force is equal to mass times acceleration to see that our object will accelerate as it falls. Here's a video of my object falling. You can see towards the end my crumpled up piece of paper seems to stop accelerating and finds a constant speed. After putting my video in Tracker, you can see that the data follows this observation. Towards the right side of the graph, the position versus time slope becomes straight, indicating a constant terminal velocity. As you can see here, the model where Fnet equals Fg does not include drag. Therefore, the only force acting on the system is the force of gravity, and the ball continues to pick up speed as it falls, which is why the slope remains curved throughout our time interval. When drag is included in Fnet, which I did in GlowScript by adding a drag force to the force of gravity, the ball reaches a terminal velocity. This is because the drag force is applied on the system in the opposite direction of motion, and eventually is as strong as the force of gravity, meaning that the net force becomes zero and the object stops accelerating. Here you can see that the best prediction between the two computer models is the model that includes drag force. The model without drag force allows the object to move much further in the same amount of time because there is no opposing force on it. Our computer is not perfect, however, because it does not have the exact same slope throughout the entire timestamp. The model that includes drag force will best predict a terminal velocity. A terminal velocity can only occur when the net force acting on the system is zero. Without drag, there is only one force acting on the system in the same direction as the motion, and therefore the object will continue to accelerate. With drag force, however, there is an opposing force that can eventually equal the force of gravity, and because the two forces are opposite in direction, they will cancel each other out, and therefore the net force will equal to zero, which means that the acceleration will also be equal to zero, meaning a terminal velocity will be found. If the initial velocity is different, for example, if the ball is thrown rather than dropped, the terminal velocity will remain the same. This is because terminal velocity is affected only by the mass of the object and the environment surrounding the object. As you can see here, an object that is thrown with great force first slows down and then quickly achieves the same terminal velocity as the object that was dropped from rest of the same mass.